Hey everybody, in this video I'm going to tell you how to come up with a molecule's molecular geometry, otherwise known as the molecule's shape, using a theory called VSEPR Theory. We're going to use the molecule SF4 as an example. Let's get started. The first thing you need to do is draw out the Lewis structure of the molecule. Just to save time, I'm not going to focus on all the detailed steps of that. We'll just set it up really quickly. As you start distributing all of your valence electrons in this molecule, it looks like this. And after all of that, there should be 2 electrons left over, which then get added as a lone pair on the sulfur atom. So this is my completed Lewis structure. As always, a Lewis structure does not show the actual shape of the molecule. To come up with the actual shape that this molecule would have, we have to first count the number of domains that the molecule has. Now, a domain can be one of 2 things. First thing a domain can be are what's called bonding pairs, otherwise known as simply bonds that surround the central atom. So that's one thing we're going to look for surrounding the sulfur, is how many bonds it has. Another thing that a domain can be is lone pairs surrounding the central atom. So if we go ahead and count those now, I'll circle them in green as we go. This bond to the sulfur counts as 1 domain. This bond would be 2, 3, and 4 domains, just as the bonding pairs give us. There's also lone pairs, and we have one of those on the sulfur as well. So this little lone pair that I crammed in here, that counts as a domain as well. And I now know that this SF4 molecule has 5 total domains. And that's the key, because it's those 5 domains that are going to define the type of shape that this molecule takes on. And that's really the key with VSEPR theory, is there's lots of different complicated shapes that can emerge, but when it comes down to it, there's really just these 6 possibilities that I have shown at the top of the video screen here. And which of those 6 shapes the molecule will take on depends on that domain quantity. We've got simple linear diatomic molecules, which this is not. 2 domains, which this is not. 3 domains, 4 domains. I'm crossing all these out because this molecule has 5 domains. This guy down here in the end would be for 6, which we don't have in this case. Since this molecule has 5 domains, those 5 domains are going to go in this shape right here. It's called trigonal bipyramidal, but the whole process is going to start with me kind of using this like a template. And that's how I tell students to think about VSEPR theory, is we've got these 6 different templates. You just want to be able to sketch that out and fill in whatever those pieces are. So let's start filling out the pieces of my 5 domain template. Of course, at the middle is the central atom sulfur. Next, let's put in the lone pair. Now, normally on any of these other different shape templates, it does not matter where you put the lone pair, but with this 5 domain shape, it is unique in that it matters which of these positions you put that lone pair. I have that outlined here in this text, although it's very small, so you probably can't see. But there's actually 2 different types of positions in this 5 domain shape. They're shown up here in different colors, and maybe I'll color code my sketch here too. There's these blue positions that are called equatorial positions, and then there's these green ones that go straight up and down. Those are called axial positions. Let me erase this purple coloration so I can color code those same things on my sketch. We've got these 3 equatorial positions in dark blue and the 2 axial positions in purple. And when you're putting in lone pairs, those lone pairs have to go into one of these 3 equatorial positions in blue. The reason for that is just space. Lone pairs are large, they repel the other domains a lot more. They need as much room as they can possibly get, and these equatorial positions have more room. So this is where I have to put my lone pair, any one of these 3. My recommendation is to put the lone pair in on the far left-hand one, just because it's going to be easier to see the shape that emerges. The point is, I've got one of my 5 domains filled out, the lone pair, in one of these equatorial spots. The other 4 domains are reserved for the fluorine atom, so I can go ahead and put those in as well. And now that I've got this sketched out, the whole idea of being able to draw is that it's a little bit easier to see the shape that we have just drawn out. This particular VSEPR shape is one called seesaw, because it looks like if you sat on this fluorine and this fluorine, if this was like a playground toy, right, it might actually rock back and forth like a seesaw. Maybe I can even grab an image of that and flip it on its side so it's easier to see. So here's that same molecule just flipped on its side, so you can maybe see the seesawness, right? Person 1 sitting here, person 2, if I could draw, sitting here, and it would then rock back and forth. Okay, so there's the seesaw aspect, and that's my favorite way of coming up with molecular geometries. That also wraps it up for this video. Thanks a lot for watching.